Thank you very much for the introduction. First of all, I'd like to thank Professor Ito and organizers, his group members, for organizing this workshop. And my title is here. I'm going to talk about another topic in semiconductor spintronics and magnetic semiconductors. Iron-based N-type ferromagnetic semiconductor, indium iron arsenide, and heterostructures. And this work has been done with these people in my group at the University of Tokyo. Dr. Pham Nam Hai is a research associate, and Reduk Ain and Daisuke Sasaki, these two are grad students. And one of the important goals in this field is to create materials and devices using the charge and spin degrees of freedom. For example, by using semiconductor device functions and also ferromagnetic device functions, we may be able to create something new system for the future information technology and electronics. And these are the examples of proposed devices. One is a spin Mosfet, which is proposed by our group a few years ago. And this is basically a silicon Mosfet, but we have two ferromagnetic electrodes, source and drain, so that this is a transistor, so transistor characteristics, but also we can have spin-dependent transistor output. In parallel magnetization, we see large transconductance, and in antiparallel magnetization, the transconductance should be low. So we can change the transistor characteristics. And another example is a spin bipolar transistor, which is proposed by Fabian and co-workers in 2004. This is also a transistor structure, but bipolar, and consisting of PN junctions and ferromagnetic semiconductor heterostructures, which will show the similar transistor type and spin-dependent output characteristics. And these devices could be used for non-volatile memory and non-volatile logic, and also reconfigurable logic functions. So to realize this kind of spintronic devices, we need ferromagnetic semiconductors. So along this line, there are many studies have been done on manganese-doped 3,5 ferromagnetic semiconductors. So in the previous lecture, Professor Ono showed many nice results on manganese-doped 3,5, and especially indium manganese arsenide and gallium manganese arsenide are the prototype ferromagnetic semiconductors. However, there are some problems in such manganese-doped 3,5. First, there are only p-type materials because manganese is an acceptor in 3,5. And there is no reliable N-type ferromagnetic semiconductors. And as you know, all of semiconductor devices, diodes, transistors, LEDs, they all require both N-type and p-types. And second, Curie temperature is still lower than room temperature due to small exchange energy. And also, there is no agreement on the mechanism of ferromagnetism. For example, there are two models, valence band conduction model, and the other one is the impurity band conduction model. So we believe that the impurity band is playing a very important role in understanding ferromagnetism and band structure in this kind of material. But if it is so, band engineering is more difficult because controlling impurity band is more difficult than controlling the valence band or conduction band. So in this talk, I'm going to talk about iron-doped semiconductor, ferromagnetic semiconductor material. In general, there are some prospects or expectations in iron-based material. In general, iron-based compounds, including metallic compounds, have high TC due to large exchange energy. And if iron is doped in 3,5, iron should be 3+, then it supplies only local spin, not carriers, not electrons or holes. So it may be able to create both p-type and n-type ferromagnetic semiconductor by independent chemical doping, so that we can control both local spin and carriers. And another expectation is that in this material, I'm going to show you later that electrons are not in the iron-related impurity band, but in the conduction band. So it may be good for modeling ferromagnetism and spin-dependent band engineering. So these are the motivations. And this is the outline of my talk. I'm going to show some basic properties of n-type indium iron arsenide and quantum wells and heterostructures. So first I'm going to show the MB growth and structural characterizations, and then MCD spectra to investigate the band structure and magnetic properties, and transport, magnetization, and magneto-optical imaging to characterize the ferromagnetic domain structure in this material, and also thermoelectric Seebeck effect to confirm the n-type conduction, and also estimate the effective mass of electrons and the Fermi level position. And if I have time, I'm going to talk about the extension of the study, quantum wells and heterostructures. So we have observed quantum size effect in very thin heterostructures, including indium iron arsenide, thin film. And by etching the top layer of indium arsenide grown on top of indium iron arsenide, we can control the position of electron wave function, and then we can control the ferromagnetism in this material and summarize. So first I'm going to show the growth, and this is a sample structure we have grown on gallium arsenide semi-insulating O1 substrate by using molecular beam epitaxy. First, we have grown gallium arsenide buffer layer and indium arsenide buffer layer at high temperature, 500 and 580 degrees. And after growing indium arsenide buffer layer, we obtained a smooth surface. So the lattice mismatch between the two materials is relaxed. And then on the atomically smooth surface, we have grown indium iron arsenide, 100 nanometer thick film at lower temperature, 236 degrees. So this low temperature is necessary to incorporate iron up to a few %. And in most of the samples, we have doped beryllium. Well, at first we expect to grow p-type material, but we found that at this low temperature, beryllium act as double donors, not acceptors, because beryllium are in the interstitial site. And this interstitial beryllium work as double donors, as already reported in other materials, like as nitrides or silicides. So the same thing happens in this material. And finally, we have grown indium arsenide cap layer at low temperature. So these are the sample list. Series A1 to A4, we fixed the iron concentration at 5%. And by changing the beryllium concentration, we changed the electron concentration from 1.8 times 10 to the 18th to 1.8 times 10 to the 19th. And series B, we fixed the iron concentration here 8% and here 9.1%. Only this sample, we don't dope beryllium, but these are doped with beryllium. So we changed the electron concentration from 1.3 times 10 to the 18th up to 2.8 times 10 to the 19th. So we can control both ion concentration and electron concentration independently. So this is a TM cross-sectional image taken from one of the samples with ion concentration 9%. And at the same time, we have measured atomic concentrations of each different point in the film by EDX measurements. And these are the results. And in all the different positions, iron concentration plus indium concentration is equal to the arsenic concentration. So this means, although we have some fluctuations of iron concentration depending on the positions, so this means iron are on the indium side. Iron replace indium. And this is read pattern during the MB growth. We see only the zinc blende type structure. And this is a high resolution TM lattice image taken from along gallium arsenide 110 axis. And even though we have 9.1% iron concentration, which is very high, we see only the zinc blende structure. So in all over the film. So this is a zinc blende single crystal structure. We see no metallic iron or no other intermetallic compounds. So then we measured mobility as a function of temperature. So this is the results of one of the samples, the same sample with the previous TM slides. Iron 9.1% without barium, but this is N-type. And if the mobility is dominated by ionized impurity scattering, the mobility is expressed this way. So the exponent gamma should be at least 1.5. But if it is dominated by neutral impurity scattering, mobility is almost temperature independent. So gamma should be nearly 0. So experimentally at low temperature, the mobility is almost temperature independent. So in this material, neutral impurity scattering is the dominant scattering mechanism. So iron atoms doped in indium arsenide are in the neutral state, iron 3+. So next we measured magnetic circular dichroism, spectra, and its magnetic field dependence. So MCD is basically the difference in optical response, reflection or absorption between the two circular polarizations. Well, this is a band structure of semiconductor zinc blende type material. When we apply a magnetic field, each conduction or valence band, each band spin split like this. And due to the selection rules, there is a difference in optical transitions between the right and left circular polarized light. So we see the difference. So we mainly use reflection MCD. And our reflection MCD intensity is expressed in this way. So basically, we measure the difference in optical reflectance between the two circular polarizations, right and left circular polarizations. And reflection MCD is also expressed in this way. This term is basically the Zeeman splitting, which is proportional to the magnetization of the material. So we can measure the magnetic properties. And also, MCD includes this term, which is the energy derivative of reflection spectra. So from this term, by measuring the spectra, we can get some information on the band structure of the material. So basically, we can detect the band edge spin splitting due to exchange interaction. So by measuring the MCD spectra, we can distinguish whether this is an intrinsic ferromagnetic semiconductor, indium iron arsenide with a zinc blende band structure, or the magnetic signal comes from iron-related nanoparticles. So this is a very powerful method. And we have grown 2 reference samples to compare. And this is iron epitaxial thin film grown on gallium arsenide, which showed a very broad and intense MCD peak. And this is due to the deep SP band to D band transition in metallic iron. And another reference sample is indium arsenide non-magnetic substrate, which shows a very sharp MCD peaks, E1, E1 plus delta 1, E0, and E2. These are the critical point energies due to the zinc blende type band structure. And then we measured, for example, this is the MCD spectra of indium iron arsenide, iron 8%, with a carrier concentration, electron concentration 2.8 times 10 to the 19th. And we see this big MCD peaks at each critical point energies due to the zinc blende band structure. So in all the indium iron arsenide shows the enhanced peaks at these critical point energies due to the indium arsenide type, zinc blende type band structure. So there's very different between the 2 materials, iron and indium iron arsenide. So MCD spectra is like a fingerprint of a material. So by investigating the spectra, we can judge whether the sample is iron-related materials or indium iron arsenide, zinc blende semiconductor. So our sample is this case. Indium iron arsenide is intrinsic ferromagnetic semiconductor with a zinc blende type band structure, and the signal is not coming from iron-related nanoparticles. So this is MCD spectra of our samples. We show 2 series of samples. One is indium iron arsenide with iron concentration 5%, and this is 8%. And we changed the electron concentration from 1.8 times 10 to the 18th here up to 1.2 times 10 to the 19th. So with increasing the electron concentration, we see the enhancement at these critical point energy peaks, E1, E1 plus delta 1, E0 dash, and E2. And by measuring the squid magnetization and also magnetic field dependence of MCD corresponding to image characteristics, we characterized that these 3 samples are paramagnetic, but this sample with higher carrier concentration is ferromagnetic. And similar results were obtained in this series of samples with a fixed iron concentration at 8%. With increasing the electron concentration, we see the enhanced MCD peaks at each critical point energy. And the sample changed from paramagnetic to ferromagnetic with increasing the electron concentration. So this shows the electron-induced ferromagnetism in this material. And to check the, whether the magnetic phase is single or not, we have measured MCD spectra of one of the samples here, sample A4 with iron 5% and 1.8 times 10 to the 19th, the electron concentration, at different magnetic fields. And then we normalized, and we show the normalized MCD peaks at different magnetic fields. And all these spectra completely overlap. So this means the magnetic signal comes from the single-phase ferromagnetism. And to double check, we also measured MCD intensity as a function of magnetic field, which is actually corresponding to the magnetization because MCD is proportional to the magnetization. And we measured this magnetic hysteresis at different photon energies. And again, we see the perfect overlap. So this again indicates the single-phase ferromagnetism. So this is another indication of intrinsic ferromagnetic semiconductor of this material. And then we measured transport. This is magnetic resistance at various temperatures. And if the scattering is dominated by spin disorder scattering at higher temperature than Tc, the magnetic resistance ratio should be proportional to the magnetization square. And also we measured Hall effect here. This is a raw data of Hall measurements at various temperatures. And the Hall resistance is dominated by the ordinary Hall effect, and which is linear, nearly linear, and negative. The negative slope means N-type conduction. But we see some anomalous Hall effect contribution. So to estimate anomalous Hall effect contribution, we subtract the linear contribution from this data, and we show the anomalous Hall effect contribution here at various temperatures. So the anomalous Hall effect, Hall resistance, should be proportional to magnetization. So the magnetic resistance ratio, which is m square, should be proportional to the anomalous Hall effect square. So indeed, when we plot the anomalous Hall effect square as a function of MR ratio at various temperatures, all the data shows a linear slope. So this means there is this type of exchange interaction in this material. And this is magnetization data of the typical two ferromagnetic samples. One is 5% iron, the carrier concentration 1.2 times 10 to the 19th. The other one is 8% and carrier concentration 2.8 times 10 to the 19th. And for this sample with lower electron concentration, the magnetization temperature curve shows the linear increase of magnetization with decreasing the temperature. And this monotonous increase data shows single-phase ferromagnetism with a Tc of 34 Kelvin. And this is magnetic hysteresis. And from the saturation magnetization data, we have 2.2 BB per iron. And when we see the higher electron iron concentration, we see some shoulder here in MT characteristics. This means there are two magnetic phases in this higher iron concentration sample. One is a matrix phase with a Tc of 28 Kelvin. The other one is a magnetic cluster phase with higher Curie temperature of 70 Kelvin and blocking temperature of 35 Kelvin. So this kind of magnetic data with a super paramagnetic-like hysteresis can be explained by the multiple domain model. It is not from the nanoparticles. So I'm going to show the magnet-optical imaging on this sample to characterize the magnetic domain structure. So this is a measurement method. On our sample, we put the garnet indicator. This is a transparent ferromagnet. This is a room temperature ferromagnet. And then we measured Faraday rotation. Well, this is the input light, and we actually detect the Faraday rotation all over the sample. And in this method, we can only probe the macroscopic ferromagnetic domains, because when we have some ferromagnetic domains, this is a stray field. So due to the stray field, this part is magnetized from down to up. This part is magnetized from up to down. So the Faraday rotation angle is just the opposite. So we see such red area and blue area, the pair of red and blue area, which is the ferromagnetic domain. And if the size is greater than the light wave, we see such domain structure in the image. However, the magnetism comes from, if the magnetism comes from the granular cases, in which the nanoclusters, magnetic clusters, the size is shorter than the light wavelength, we see no such macroscopic image. So it is possible to distinguish the macroscopic ferromagnetism from the superparamagnetism. And this is the experimental data of one of our samples with 8% iron. And we measured this magnetoptical image at 4 Kelvin, which is in the ferromagnetic state, and a zero magnetic field, which means remanent state. And we see some domain area here surrounded by the blue circles. And this is the interpretation. We see some ferromagnetic domain area at zero magnetic field. And this yellow arrows are the magnetization vector. And also we see some white area, which is paramagnetic. This is because we have some fluctuation in the carrier concentration. This area is ferromagnetic because the carrier concentration is greater than 10 to the 19th. And in some area, carrier concentration is less than 10 to the 19th because of some structural fluctuations or defects. So we see paramagnetic area. So anyway, we see directly observe the macroscopic ferromagnetism in this material. And this is the magnetic field dependence at 4 Kelvin. So this zero field image is the same as the previous slide. But we scan the magnetic field from high field, 400 Elsted. And at high field, we see almost single domain or red area. But with decreasing the field down to zero, corresponding to this magnetic field image hysteresis, starting from point A, now we hear remanent state, point E, corresponding to this image. And then we scan the field to minus direction, minus 100 up to minus 400. Again, we see a single domain. And corresponding to this point. And then go back to zero, which is point L. Here is another remanent state. So if you compare these two opposite remanent states corresponding to this state and this state, we see just the opposite color patterns. Red and blue patterns are just the opposite because this is a ferromagnetic domain. And then we measure temperature dependence at zero field. Starting from this zero field remanence state, at 4 Kelvin, we see color contrast due to the domain structure. But with increasing the temperature, the contrast becomes weak. And we completely lose the contrast at 70 Kelvin. So this means the Curie temperature of each ferromagnetic domain is 70 Kelvin, which is consistent with the previous squid measurements. So to summarize our magnetic data, this is Tc as a function of electron concentration for various samples. At electron concentration lower than 10 to the 19th, the Tc is 0. that means paramagnetic. But if you increase the electron concentration, the sample became ferromagnetic. And this is resistivity as a function of temperature. These metallic sample are ferromagnetic, and these insulating sample corresponding to the paramagnetic samples. And the threshold electron concentration to induce ferromagnetism it is 10 to the 19th, about 1 times 10 to the 19th. And this number is probably smaller than the holes of gallium manganese arsenide. In this material, although the features are very similar, but this is p-type, and the threshold hole concentration of this material is probably 5 times 10 to the 19th. But in this material, this is n-type, and threshold electron concentration is 10 to the 19th, 1 times 10 to the 19th. And then we measured thermoelectric Seebeck effect to confirm the electron conduction. And the measurement method is very simple. We apply the temperature gradient on this sample and measure the voltage, thermoelectric voltage. And this is the measured thermoelectric voltage as a function of temperature gradient. It shows a linear, perfectly linear dependence. And from this sign of the Seebeck coefficient, we confirmed N-type conduction. And also, the Seebeck coefficient is expressed in this way with this carrier concentration and density of states. We can estimate from this data the effective mass of electrons and Fermi level position. And these are the data of effective mass of electrons as a function of electron concentration for the indium arsenide N-type material and our material, indium iron arsenide. And these black and white dots are taken from this literature, which shows the effective mass of electrons of indium arsenide. And these colored dots are our data of indium iron arsenide. So we found that the effective mass of electrons of indium iron arsenide is very similar to the effective mass of electrons of indium arsenide, which is 0.03 to 0.17 M0, depending on the electron concentration. So these values are very, very small, actually light effective mass of electrons. And Fermi level is 0.15 electron volt above the conduction band bottom in this material. So this means electrons are in the conduction band, not in the impurity band. So to summarize the data of our indium iron arsenide material, we can grow zinc-blende type indium iron arsenide with iron concentration up to 9%. And all the structural data confirmed zinc-blende type structure. And iron in this material are neutral, and electrons are supplied by the beryllium double donors up to 10 to the 19th. And MCD intensity and TC are enhanced with increasing electron concentration. This means the electron-induced ferromagnetism. And we have measured magneto-optical imaging technique, and we observed magnetic domain structure. And N-type conduction was confirmed both by the hole measurements and the Seebeck measurements. And effective mass of electron is 0.03 to 0.17 M0. That means the electrons are in the conduction band, not in the impurity band. So we think that this is a new N-type electron-induced ferromagnetic semiconductor, which is suitable for spin-dependent band engineering. So for the last few minutes, I'm going to show the extension of the study, which is the quantum well and heterostructures. So we have grown this type of samples here again on gallium arsenide substrate by MBE. And here we grew indium arsenide bottom layer. We changed the thickness. And then indium iron arsenide beryllium doped layer. We again changed the thickness. And the top layer of indium arsenide. These are the sample list. The sample F is a reference sample, which is a very thick indium iron arsenide, 100 nanometer thick layer. And these are the estimated TC. So here is the conduction band profile of this heterostructure we expect. We expect that these three layers, top indium arsenide, indium iron arsenide, and bottom indium arsenide, form the quantum well because of the band offset between indium arsenide and gallium arsenide, which is 0.9 eV, and also vacuum potential on the surface, which is 4 electron volt. So first we changed the thickness of indium iron arsenide from 2 to 10 nanometer and measured reflection MCD. And this black curve is the MCD spectra of the reference sample with a thickness of 100 nanometer, which is very thick. This is a bulk-like sample. And with decreasing the thickness of indium iron arsenide, we see the blue shift of each peak of E1 and E0' and E2. So this means we see a quantum size effect in such quantum well structure. And then we measured another series of samples in which we changed the thickness of the bottom indium arsenide layer. So we changed the thickness of this layer so that the total thickness of this tri-layer L is changed from 15 to 40 nanometer. So even when we changed the thickness of the bottom layer with a fixed indium iron arsenide layer, we see the similar blue shift with decreasing the thickness. So this means electron wave function are not confined in this magnetic semiconductor layer, but confined in the tri-layer. So electron wave function extends smoothly all over the tri-layer quantum well. So this means the S-wave-like nature of the electrons in indium iron arsenide. So then, to check this feature, we did another experiment. Here is the sample structure, the same as the sample before. And then, 10 minutes? Okay. Okay. And this is a starting sample structure, which is the same as the previous experiments. And then we measured MCD after etching the top indium arsenide layer by using this wet etchant. So we carefully etched the sample, the top layer, gradually. And then if you etch the top indium arsenide layer, the thickness of the top layer is thinned. And then the wave function starting from here, and then the position of the wave function is pushed back to the substrate side, so that the overlap between the electron wave function and indium iron arsenide layer decreases. So, however, if the wave function is confined in the ferromagnetic semiconductor layer like this, then even when we etched the top layer, in this case gallium arsenide, the position of the wave function of carriers does not change so much. So we can distinguish between the two cases. This is the experimental data, and this is again MCD spectra as a function of photon energy measured at 5 Kelvin under the magnetic field of 1 Tesla. And well, this number means the etching time. That means one etching time corresponds to the etching of 1.25 nanometer. So with etching the top indium arsenide layer, the E1 and E0 peak shows the blue shift. And the intensity is decreased at the same time. And this is a substrate signal, gallium arsenide substrate signal, which shows the fixed peak. And this is the intensity of E1 peak. And during the etching of the top layer, the intensity doesn't change. And when we start etching the indium iron arsenide, the intensity of E1 shows the decrease. This is very natural. So, and this is the Curie temperature as a function of etching times. So, as we expected, the Curie temperature already start to decrease during the etching of the top indium arsenide layer, like this. And then when we start etch the indium iron arsenide, the Curie temperature further decreased down to 0. So the important point is that although we etched only the top indium arsenide layer, the TC is decreased from 22 Kelvin to 10 Kelvin here. So then, in order to compare with the calculation, we have calculated the quantum well state and potential by using the self-consistent calculation method. So we solve the Poisson's equation and Schrödinger equation self-consistently. And here is the assumption. The Fermi level is pinned at the surface here, and mid gap of gallium arsenide band gap on the substrate side. And we assume the spin polarization in this material was 0, neglected. And the activated donor density ND, which is here, is taken as a fitting parameter. And also, we use these parameters estimated by this literature. This is the effective mass of electrons and band offset and surface spinning position. And this is the calculated results. So before etching, we have this type of quantum well potential. And the first subband and second subband are filled by electrons. And Fermi level position is here. Here is the electron distribution adding these two subbands. So we have significant overlap between the carriers and indium iron arsenide. And this is the fit results. This is E1 blue shift. These red data are the experimental data, and the curves are the fitting. This is a fit parameter. So we show a good fitting. And with etching the top layer, the thickness of the quantum well is thinned. And then this is the electron distribution consisting of these two wave functions. So the electron distributed here at first, but with increasing the etching thickness, the total thickness is decreased, and then the electron wave function is shifted towards the substrate side, so that the overlap between indium iron arsenide and the electron carriers are decreased, so that the Curie temperature is decreased. So there is a theory to predict the TC in such quantum well based on the gallium arsenide and gallium manganese arsenide heterostructure. And this was the paper by Lee and McDonald's group. And they showed this TC based on the mean field model. And these are the fitting parameters. And although this is a different material, we applied this theory and tried to explain our experimental results. by using these fitting parameters. JSD is the SD exchange interaction energy, and this is the threshold electron density of ferromagnetism. And this is the Curie temperature as a function of etching depths, and these red data are the experimental results, and these blue lines are the calculated TC based on this theory. So we can fit the results very well, but we have to assume that the SD exchange interaction energy in indium iron arsenide is very large. So in terms of JSD, it is 0.25 eV nanometer 3. And in terms of N0 alpha, it should be 4.5 eV. This is unexpectedly large for narrow gap semiconductors. Conventional data is like this. In 2,6 DMS, N0 alpha is 0.2. And even for P-type gallium manganese arsenide, N0 beta is 1.2 eV. So this fit parameter is very large. So this means probably the challenge of the present challenge, this results challenge the present understanding on DMS, especially on SD exchange interaction. But if this is true, if we have large SD exchange energy in this material is very promising for high TC ferromagnetic semiconductors. If we can prepare a good material with much higher electron concentration. So to summarize, we have observed quantum size effect in the thin film quantum wells and heterostructures. And from the experimental results, we confirmed electrons exist in the conduction band of indium iron arsenide. And also we can change the Curie temperature by etching the top indium arsenide layer and by moving the wave functions inside the tri-layer quantum well. And we show unexpectedly large SD exchange interaction in this material. So this may require the modification of existing understanding. So we hope that this is a very promising material, and probably the electronic structure could play an important role in the ferromagnetic transition temperature. Thank you very much.